All right. So I want to finish. We didn't get to this part here where we consider the combined gas law. And I did show you a bunch of, Charles' law, Montan's law, Avogadro's law. They can all be combined into just one gas law that we can use. And then instead of memorizing all four of those, if you just know two of these gas laws, they should get you through a lot. So one is our ideal gas law. PV equals nRT, and again, we use this gas law when we're just trying to describe some gas. I want to know something about it. What's its volume? What's its temperature? How many moles? And we use this when there is no change and we're just trying to describe some gas. Then we can also use this one here. It's slightly different than this because I've also included the number of moles here. And whatever's constant here, we're not going to need. Whatever's left is going to be the formula that we use. I might backtrack and go to a couple more problems. Let's see what this has here. Ammonia, so 200 liters, 0.25 liters. Find the volume of the sample. So I think I'm going to back this up and let's consider a different one here. Let's see here. Yeah, let's take a look at this one. So we're not really sure which one to use here, and you kind of have to pick to see which one that you need. Or you can just set this one up here. What's the temperature of a 650 or 635 ml sample? So here I have some sample that is 635 milliliters. And this sample here is at 1.1 atmospheres. It occupies at 298, let's see, what's the temperature? If it occupies, I think my initial and final. Let's go here. So we need volume, pressure. I do have some temperature here. So if this is at 298 Kelvin, it's at 1.1 atmospheres. What is the temperature? I'm just trying to determine what's initial and what's final. What is the temperature of a 635 milliliter sample of ethane at 1.5? It occupies 400. Okay, so we're going to say the 405 is our initial. So our initial value here is going to be 405 milliliters. It's at 298 Kelvin. And our pressure is 1.1 atmospheres. What is the temperature at this volume? So I have all these initial and all these final values here, right? Well, if I want to know which one of these we should use, well, I can just use this. Did it talk about any moles changing? No. So we can just consider, we can assume that moles was consistent. The number of moles did not change, and those are consistent. Pressure here also didn't change. So that means we don't need to consider pressure. So now if we clean this up, this is the formula that we're going to use in order to determine what that final temperature is. I didn't need to do, which one is it up here? I didn't need to memorize all four. I just needed to know this one over here. So let's do this one more time. We're not going to solve this. We spent some time yesterday solving those and we need to move on. But let's move on to another problem. And we're going to use the same setup we did. We have P1 V1 over N1. T1 is equal to P2V2 over N2T2. All right. Let's see here. A sample of nitrogen occupies, so here, because it occupies it, the volume, my initial volume is 45.0 milliliters. It is at 27 degrees Celsius, and my pressure is 600 torr. What will the pressure be if we cool it to negative 73 degrees Celsius and the volume remains constant? Well, since volume didn't change and it's constant, we don't need to consider that. It doesn't talk about the number of moles changing, so I guess that's consistent too. And our new formula to solve this is going to be P1 T1 equals P2 T2. And we have all the information we need in order to solve that. So this is how we use that combined gas law, right? Is that anything that's consistent, well, we can just simply remove that variable from our equation here. All right, stoichiometry. So we're going to review, so we're going to get into this. Hopefully we can finish it. But stoichiometry of gaseous substances, mixtures, and reactions using the ideal gas law, right? So have your calculators out. We are going to be running through quite a few calculations here when we try and understand the stoichiometry here. So the density of gas. So we know the formula of density, right? Density is equal to some mass over some volume. Mass over volume. And from our ideal gas law, we know that pressure, right, PV equals nRT. Well, I'm going to rearrange this really quick, and I'm going to say volume is equal to nRT over P. All right? And I'm going to use some initials over here. I'm going to erase the mass over volume. I'm just going to put M over V. So here, this volume is equal to this volume here. And we can put this into the equation over here. So if we do density is equal to mass over nRT over P, and then we want to clean this up a little bit because it looks a little awkward to have a fraction over a fraction. So if we clean this up, we're going to have mass over nRT. So here's a new formula for density. And then if we take a look at one more thing here, because we still have to clean this up just a bit more. Mass over the number of moles. From the periodic table, we get grams per mole. Some mass over some amount of moles. So this can now be considered molar mass. So we're going to clean this up. We're going to use this capital M here. Actually, it's not a capital. I think it's like a fancy looking M. It's like, I don't know. I'm not really good at curves, but it's some fancy looking M. And then we're going to go nRT is equal to density, right? So the molar mass of some substance times the pressure, so let me get rid of this N here, some molar mass times the pressure over the RT over here. So this is going to be our one of our new formulas that we're going to use here. All right. So what is the density of molecular nitrogen at standard temperature and pressure? Does anybody remember what the standard temperature is? Rhymes with zero. 0 degrees Celsius, right? 273.15 Kelvin. Right? So here, pressure, atmospheric pressure, 1, right? That's standard temperature. So we wanted to know about molecular nitrogen. Molecular nitrogen is N2. Let me erase some of this up here. So molecular nitrogen, this is 14.01 times 2, so we get 28.02 grams per mole of N2. So what is the density of this? Well, our density is going to equal this molar mass, so we're going to get 28.02 grams per mole. And at atmospheric pressure, this is going to be 1 atmosphere, STP, over our rate constant, 0.08206 liter atmospheres per mole Kelvin. And we're going to multiply that by the temperature of 273.15 Kelvin. So now we're going to see these units go away. Let's cancel out our units. Let's say moles cancels moles. Atmospheres cancels atmospheres. Kelvin cancels Kelvin. And this is gonna be in grams per liter, right? And density it is mass over volume, so we can use that there. It's not necessarily asking us to convert it to milliliters, so I think we're just gonna go ahead and leave that in liters. But we can now calculate this out. So 28.02 divided by 0.08206 divided by 273.15.
1.25.
We get 1.25 grams per liter, and we could convert this into milliliters. I think we'll just stop here though, but this is going to be our density. So the formula does come in really handy when we're trying to calculate densities of gases. So many emails. All right. Let's see if we have another problem now. All right. So let's determine the density. So we have different temperatures, different pressures now, but the formula is not going to change. We're still going to use that particular formula. Is that our density is equal to molar mass over pressure, and this is going to give us some density of some gas here. And I think this time let's calculate this in milliliters. So we'll throw that in as well. So what's the density of molecular hydrogen? So when it talks about molecular hydrogen, this is hydrogen. This is molecular hydrogen as a molecule. So this is 1.01 times 2. That's going to be 2.02 grams per mole. So what is our density? Our density is going to equal 2.02 grams per mole. We're going to multiply that by the pressure, but because of this rate constant here, liter atmospheres per mole Kelvin, we do have to convert 760 torr into atmospheres so that we can use this rate constant here. So we're going to put in, let's see, we have 760 torr. We're going to convert this into atmospheres. So the definition, there's 760 torr in 1 atmosphere. And then we're going to do our rate constant, 0.08206 liter atmospheres per mole Kelvin. I'm going to do a conversion from liters to milliliters here. So we're going to say for every 1 liter, there is 1,000 milliliters. And then finally our temperature, which does have to be adjusted. We have 17.0 to 73.15, 5, 1, 10, 9, 2, so 290.15. So now we have everything we need. Let's cancel our units out. So liters cancels liters, moles cancels moles, torr cancels torr. Oh, atmospheres cancels atmospheres, Kelvin cancels Kelvin, and we're now going to be grams per milliliter. Because it's such a short lecture day, I'm going to calculate these. So 2.02. This is going to basically cancel each other out, so I'm not even going to bother with this. So 2.02 divided by 0.08, 0.08206.
8.48 times 10 to the negative
8.48, is that what was it?
Yeah.
Yeah, thanks for verifying that. Yeah. It is going to be 8.48 times 10 to the minus 5 grams per milliliter. Right? So that's going to be our density there for that particular gas. All right. Yes?
Why don't we use the R in the last set of problems, like the PV over NT? Where does the R go?
So when we're looking for some change in gas, right? We're not describing the gas. Okay? When we're describing properties of gases, is we need that rate constant. But if we're doing some change, if I just want to know what the pressure changes or what the volume changes, what the temperature changes because something increased or decreased, there's no need for that particular, for the R constant there. Okay? All right. This is also another formula that's derived to help us determine molar mass, right? So along with this one here, now we're going to have this molar mass is equal to mass RT over P V. So two different formulas. One describes density for us. The other one we can use in order to calculate molar mass. That's what this curved M here, right, is that this is molar mass in grams, right? Molar mass in grams per mole. All right. So let's see if we can get through this one. So cyclopropane, a gas that's once used with oxygen as a general anesthetic, is composed of 85.7% carbon, 14.3% hydrogen by mass. Find the empirical formula. 1.56 grams of propane per oxygen. What is the molecular formula for this? All right. Wow, that's a lot of information there. Okay, let's get through this one here. So we don't need this here. So in order to determine the molecular formula, right, is we need to determine the number of moles, right? So this kind of combines what we've learned in previous chapters here in order to determine what the molecular formula is here. So let me just write down some information. So currently we have 80, is it 85? 85.7% of it is carbon. But instead of using the percentage, what can we do? Grams, yeah. We can say, because we're going to assume we have 100 grams. So we have 85.7 grams of carbon, which means that we have 14.3 grams of hydrogen. We're going to convert these into moles. So carbon is 12.01 grams per mole. Hydrogen is 1.01 gram per mole. And let's consider what these moles are. So 85.7 divided by 12.01, 7.14, and then we have 14.3 divided by 1.01, and that gets us 14. Let's go 14.16. So these are the amount of moles that we have. Now, because this one is a smaller one, I'm going to divide this by 7.14, and I'll divide this by 7.14. This is going to come out to 1. And without a calculator, I already know that this is going to be about 2. So our empirical formula here is for every 1 carbon, we have 2 moles here. Find the empirical formula, so we did that. Now we need to find the molecular formula. So here, if we have 0.156 grams of cyclopropane, so let's get that information on the board. So with cyclopropane, is 1.56 grams. And our molecular formula here well, let's get the molar mass of this. We have 12.01 plus 2.02, and that's going to give us 14.03 grams per mole. Now, if I know the molar mass, and this is what I'm trying to figure out here, I want to know what the mass, what is the mass of this? So let's rearrange this formula here in order to determine what this mass is. So we're going to take the molar mass times pressure times volume divided by the rate constant divided by the temperature is equal to this. So we good with that? This is just a little bit of algebra here. All right. So our molar mass, we determined that was 14.03 grams per mole. So 14.03 grams per mole. Our pressure is 0.984 atmospheres. 0.984 atmospheres times a volume of 1 liter over 0.08206 liter atmospheres mole Kelvin. And they give us a temperature of 50 degrees Celsius, so 273 plus 50, it's going to give us 323.15.
Yeah.
All right. So now that we have all this information, let's make sure we cancel good. So liters cancels liters, atmospheres, atmospheres. Kelvin cancels Kelvin. Moles cancels moles. And we are just simply left with some amount of grams here. So let's go ahead and make this calculation. .03 times 0.984 divided by 0.08206 by 323.15 0.521 grams. All right. So if this is the mass of cyclopropane, does anybody need this portion here because I'm going to be using it? We're good? All right. .56 grams of cyclopropane over this empirical formula, 0.521 grams, is equal to what? Do we need a calculator? 15, right, divided by 5 is 3. So the empirical mass is 3 times smaller than cyclopropane. So if we take CH2 and we multiply that by 3, we get C3H6. This is the molecular formula for cyclopropane. Right? So a lot of work going into that, right? So you practice these steps for the exam so you're able to do it when you see it on the exam, right? We're good. Let's see, let's do one more here. We're going to figure out what's the, so it's going to be the same formula here. We've rearranged this so that mass, mass is equal to molar mass times pressure times volume over the rate constant times temperature. So this is what we rearranged it to. And let's calculate another problem here. All right. So we have 92.3 grams of carbon, and we're going to say we have 7.7 grams of hydrogen. Let's convert these into moles. This is 12.01, 1.01 grams per mole, grams per mole. So 92.3 divided by 12.01, and we're going to get 7.69, and then let's go 7.7 divided by 1.01, we get 7.62. This one's smaller, 7.62. This is equal to 1. If we divide this by 7.62, it's pretty close to equaling 1. So the empirical formula here, our empirical formula is CH. All right. So now we have this other information over here, and we'll start putting this together. So the mass, we need the molar mass of this first. So this is going to be 12.01, 1.01, 13.02 grams per mole. All right, so this is our our empirical mass that we're going to use here. So that's going to be 13.02 grams per mole. We're going to multiply that by some pressure of 1.15 atmospheres. And we need some volume of 1 liter. over our rate constant, 0.08206 liter atmospheres, mole Kelvin. And this is 59.5, so 273, 59.5, 5, 6, 12, 13, 332.65. Our units will all cancel out, so we can just go ahead and calculate this. 13.02 times 1.15 times 1. Let's see, divided by 0.08206 times 330. Nope, divide, I'm so sorry. 6 divided by 332.64. 0.549. We'll say 0.549. 0.549 grams of our empirical formula. Now, if we take that, they give us the amount of the sample. So acetylene is 1.10 gram. So we're going to take 1.10. We're going to divide it by 0.549. This roughly comes out to 2. So we can do CH times 2, C2, H2. And here's empirical formula, molecular formula. Right? All right, so we have some time to get introduced to Dalton's law here. So Dalton's law is a law of what we consider partial pressure, right? Sometimes gases mix and they don't react, right? Like our air. Our airs consist of nitrogen, oxygen, argon. There's all these trace gases, and each one of those has their own particular pressure, right? And then we can combine those into just one total pressure. Right. So we simply just take whatever pressure A is, B is, C is, and then we get our total pressure by adding those all up together. So these are what we call partial pressures, right? So P sub A is the partial pressure of A, P sub B is the partial pressure of B, so on and so on, and we get all these partial pressures, add up all the partial pressures, and we get the total pressure. Okay. So in kilopascals, whatever this is 300, this is 450, this is 600, this is the partial pressure, but if we add all those partial pressures up, then we get the total pressure of whatever that particular mixture of gas happens to be. So what is the partial pressure of each gas here? What are we looking at? What's the total pressure in atmospheres? So we have a 10 liter, we have a number of moles at 35 degrees. Okay, so here, are we making any changes to the gas? Are we increasing or decreasing its pressure, temperature, or volume? No. Right, so we're just going to use the ideal gas law. So our ideal gas law is PV equals nRT. So the pressure is equal to nRT over V. So now we have to do this for each one of these gases that's listed here. So what's the partial pressure of each one of these gases? So let's take hydrogen first. So the pressure of hydrogen is equal to the number of moles of hydrogen, which happens to be 2.50 times 10, is that to the minus 3? Yeah, to the minus 3 moles. Our rate constant, so times 0.08206 liter atmospheres, mole Kelvin, times a temperature at 35 degrees, 308 times 308. Oh, I'm going to put 0.15 here. 0.15 Kelvin over, is that 10 milliliters or liters? Good, 10 liters. So this will give us the partial pressure of hydrogen. I'm going to set these up because and then maybe you guys can start calculating them. So that gives us the partial pressure. Now we need helium and also neon. So the pressure of helium is going to be 1.0 times 10 to the minus 3 moles times 0.08206 times 308.15 over 10.0, and the pressure of neon is equal to 3.00 times 10 to the minus 4 times 0.08206 times 308.15 all over 10.0 liters. All right, does anybody have a value for the top one here? Anybody have the next two?
Pressure of helium is 2.53 times 10 to the negative 3.
And lastly, what is it? I'm sorry.
7.59 times 10 to the minus 3.
10.95?
Erased.
I'm sorry.
Oh, 7.59 times 10 to the minus
7.95
times 10 to the minus 4.
times like this?
Minus 4.
Well, minus 4, thank you. All right, like this?
Yes.
All right. So our total pressure,
0.59, sorry.
5.9?
Yes.
No, that's okay. My hearing's not that great today. My ear's pretty clogged. So to get the total pressure here is we're simply just going to add all of these pressures up together. So can somebody add this, this, and this together, and that's going to be our total pressure. And this will be in atmospheres.
Times 10 to the minus 3.
Like this? All right. All right. So we could, calculate this partial pressure. So if we mix all these gases together, put them in some 10-liter container, is that this would be our pressure over here in that particular container. All right. What is this one asking here? What is the total pressure in the flask? We have some flask, a new number of moles here. All right. So yeah, let's go ahead and we'll set this up again. And it is the same process. We just have new values now. All right, so here, the pressure of, which one will we have first here? N2? So the pressure of N2 is we have 0.0388, 0.0388 times 0.08206 times our temperature at 25 degrees C, so this is 273, 25 gives us 298.15 Kelvin. And the volume of this container is 5.73 liters. 5.73 liters. The pressure of carbon monoxide, is it just those two? Nope, H2 as well. So hydrogen, molecular hydrogen as well. So we're going to have 0.080, nope, 0.147. And finally, for hydrogen, it is 0.0803. Anybody get these two here?
I got for CO 0.627. Oh, 28.
Okay, I think we're good with just three. Anybody get the first one?
It's 0.165.
And then we'll just simply add all this up. So what is this plus this plus this for our total pressure in atmospheres? So total pressure is 1.135 atmospheres, right? Why was this one larger and the other one was so small, right? Well, it relates to the number of moles here, right? Our moles here, we have a really tiny amount of moles. Small amount of moles, small amount of pressure. Larger amount of moles, larger amount of pressure, right? And I don't know if we have, well, let me talk about introducing this. We'll continue this next Wednesday. But here, you know what, no, I think we'll just probably cut it off here before we get into this over here. So we do have some more to continue next Wednesday. But other than that, I do have to end the class because I have a meeting in about 7 minutes. No.